Let's recap a few things before we get started with some examples of hypothesis testing for mu when sigma is not known. So remember here, we're saying that sigma, this population parameter, sigma, is not known to us. We know that the population exists, this population of y, whatever it is that we're trying to measure about the population. We know it exists, we know there's a distribution, but we don't know what mu is, and we don't know what sigma is, okay? And it's mu that we're wanting to do hypothesis testing about. Is mu equal to some value, is it not equal to some value, and so on. But we don't know what sigma is, and that would be a common situation. How would we not know mu, but somehow know what sigma is, okay? So we're going to assume that we don't know both mu and sigma. And we're going to have to use S as an estimator of sigma, okay? We're going to use the sample standard deviation as an estimator for the population standard deviation, okay? And we said that whenever we know sigma, we can use a z-score in our test statistic. Our test statistic is going to be is going to follow a z-distribution. The critical value approach works with a z-distribution. The p-value approach works with a z-distribution. In this case, when we know S and not sigma, we're going to have to use a t-distribution, okay, for a particular degrees of freedom, okay? So our test statistic, t naught, is how different is y bar from the estimated value or the hypothesized value in standard deviation units, where standard deviation here is measured with S. Okay, we don't know sigma. We're using S in place of sigma. Okay, so again, let's recap what we know about this test statistic. It is how different is the evidence, okay, our sample statistic, our sample evidence. How different is that sample evidence from the hypothesized value? If those two things are really different from each other, then we want to know about it. Okay? If our sample is so much different than the hypothesized value in standard deviation units that we need to reject the null, then this test statistic is going to tell us that. Okay? And so for the critical value approach, we have a t distribution with a particular degrees of freedom. Okay? Its mean is 0. And let's say we have this set of hypotheses. H naught is mu is equal to mu 0. H1 is mu is not equal to mu 0. Okay, so we have a two-tailed test that says that the rejection regions are out in the tails. Okay, how can the mean not be equal to mu 0? Well, it could be bigger than or it could be smaller than. Okay, so that's why we have a two-tailed rejection region. And we calculate this test statistic. If this test statistic lies out there, what does that mean? That means that y bar must have been a lot bigger than mu 0. Okay, a lot bigger means significantly bigger, bigger enough such that we would conclude that those two things are different numbers. Okay, or if it lies down here, what does that mean? That's a negative value of t. That must mean that y bar is smaller than mu 0, significantly smaller, small enough that we would reject the null and conclude that the mean is something other than this hypothesized value, mu naught. If the test statistic lies anywhere in here, in the non-rejection region, we have no reason to believe that the mean is something other than mu 0. Okay? So that's a quick demonstration of the critical value approach. The p-value approach for this set of hypotheses would go something like this. We calculate our test statistic. Let's just say it lies here, for example. Okay. We calculate the area in the tail above the test statistic in this case, okay, because the test statistic lies to the right of 0. We take this area, we multiply it by 2, because this is a two-tailed test. Take that area, multiply it by 2, and that's the p-value. Okay? If the p-value is less than alpha, then we reject the null. Okay? If the p-value is greater than alpha, then we do not reject the null. Okay? So what does this mean? This means that if the p-value is less than alpha, then the test statistic would be lying in the rejection region. Okay? That's what this means. If the p-value is less than alpha, then the test statistic would lie out in the rejection region. It would lie beyond our critical value if we were using the critical value approach. But we can just look at the area in the tail directly. We don't have to calculate. We don't have to find what these critical values are. Okay? We can just compare this area directly to alpha and draw conclusions. So this is the critical value approach. This is the p-value approach. This is the test statistic for drawing hypotheses or drawing conclusions about hypotheses for population means for one single population when the standard deviation of the population is unknown. Now let's take a look at a few examples and implement both of these approaches.